Here in this video, we'll try to understand KMP algorithm and how the search works in linear time. To understand this, we have taken one example. So here the text is some combination of A's and B's, and for pattern I have taken 5 consecutive A's. So our goal is to match this pattern and see whether we can find it within that text. But before we go to the actual search part of KMP algorithm, some pre-computation is required. So for KMP algorithm to work, we need to do longest prefix suffix calculation. Why that is required, that we'll try to understand when we go to the actual search part. But for now, let's see what does it mean by longest prefix suffix or LPS, and how this LPS table actually is calculated. So let's take an example. Okay, suppose we have 4 consecutive A's. So as you see this green arrow, the first 3 letters are all A's, right? And if you see the bottom arrow, last 3 letters are all A's. So this first 3 letters is a prefix and this last 3 letters is a suffix. But prefix matches with suffix, right? Basically both are same. So that is our goal when we are doing LPS calculation. Basically we are trying to find out the length where the prefix and suffix is same for a particular string. Okay, so for a string with 4 consecutive A's, as I explained, the LPS value will be 3. So basically that's why I have taken 5 consecutive A's as pattern, because the LPS calculation becomes very intuitive for like the LPS value for each position will be 1 less than the actual length of the string. So let's see, when length equals to 1, the value is 0. Why? Because we have only one single A, right? And that is the whole string. There is no prefix or suffix there, so value is 0. When length is 2, we have this first A as prefix and second A as suffix, both match. That means this prefix and suffix is same. So for length 2, the value is 1. For length 3, this is the 3 consecutive A's. First 2 is the prefix, last 2 is the suffix. Prefix and suffix is same. For string with length 3, the LPS value is 2. Okay, now as I explained earlier, when length is 4, value of LPS is 3, and I have put these values in a array basically, and we'll use that LPS array when we do the actual search part. Let's move to the actual search part and see how we are utilizing this LPS thing. So while doing the search, we will start from the first position of text and first position of the pattern. So T equals to 1, P equals to 1. This is a match. So we can increment both T and P. That's what we are doing here. T equals to 2, P equals to 2. Again, text and pattern characters, there is a match. So we can just increment it to T equals to 3 and P equals to 3. Again, same thing, we have got a match. We'll increment both values, T equals to 4, P equals to 4. Again, there is a match. We increment both values, T equals to 5 and P equals to 5. But now, as you can see, there is a mismatch. Pattern character is A and text character is B. So basically here our search failed, right? So now what should we do here? Okay, Let's think about the brute force approach first. So if we are implementing the brute force approach, what we would have done, we would have moved back T to the second position and pattern P to the first position. Why? Because in brute force approach, for every position of T, we need to check whether we can find a pattern match or not, right? So we started with the first character of T and we couldn't find a pattern match. So we need to move to the second position of T, right? That's why we would decrement T to the second position. And for pattern, because we are starting in a fresh manner when T equals to 2, so we'll start from the first position of the pattern and we'll see from there whether we can get a match for all the consecutive characters, right? So if you think code wise, basically you can think of this pattern running within a inner loop, right? And it will run for the length of the pattern, and this inner loop will get executed for each position of the text, right? So basically we have outer loop which is getting incremented one by one for each position of the text, and within that outer loop we are checking whether we can find the pattern using an inner loop, right? So if you think text size is n and pattern size is m, so the worst time complexity would be big O of m into n, right? So that is quadratic, not linear. Now let's see how KMP improves on that. So I have moved to the next slide. As you can see, I have decremented P, right? But I didn't go back to the first position. Instead of going back to the first position, I have just moved P from fifth position to fourth position. And T I haven't decremented at all. T remains same, the value is 5. So why did I decrement P from the fifth position to the fourth position, right? So if you see in the bracket, I have mentioned LPS 3 plus 1. Let's go to the LPS table. This is the LPS table, right? So LPS index 3, that means the length is 4. Basically we are having a string of consecutive 4 A's. In that case the value is 3, right? So if you remember, right, we have this green arrow and we explained the thing. Here this is the prefix and this is the suffix and both matches, that's why the value is 3. Now let's go back to our current slide. Yeah, right. So we have mentioned LPS 3. Why we are doing that? So if you think in all our previous steps, what we did, we got a match, right? We matched these four characters in the pattern, right? 4 is, and as part of the previous steps, we have already matched this last 3 is, right? Which is the suffix of the LPS, right? LPS 3 basically, which is the suffix of the string with 4 consecutive is. That's what we did in our previous step. But because the LPS value is 3, that means we have 3s in the prefix also in this pattern, right? So if you see, we have 3s as prefix and we have 3s as suffix. So in pattern size is 4 basically, right? So that means because we matched 3 consecutive A's as suffix in our previous cycle, we have already matched the first 3 letters of the string, basically the prefix, in our current cycle, right? So for our current cycle, we don't need to go back to the first position because we already know what till which position we have already matched, right? That is the LPS value. So we can just go one character after the LPS value and see whether that pattern matches with the current position of t or text. So that's what we just did here. So LPS 3, basically LPS index 3 is value 3 plus 1, so that is 4, and we have moved pattern back to the fourth position, and we are checking with the same position of t. But again, there is a mismatch. So what should we do? We will follow the same procedure, but just one thing. So in our previous slide, our our substring was like with length 4. Now our substring has length 3. We have So we need to check the value of LPS 2, which is basically we need to check LPS value of a substring with 3 consecutive base, which is basically 2, right? So 2 plus 1 equals to 3. So we have moved it back to third position from the fourth position. Again, there is a mismatch because as you can see, it doesn't match with B, T remains same, and we just decrement P to 2, and again our pattern size of previous cycle just reduces. Now it becomes 2, so we check in the LPS array with index 1. The value is 1. 1 plus 1 equals to 2, so P is moved back to the second position from the third position of the previous cycle. Again, there is a mismatch. P becomes 1 using the LPS table, T remains same. But now here is the interesting part, right? So P is 1. That means we have exhausted all the options in the LPS table. We can't go beyond LPS 0, right? That is the leftmost index in the LPS table. So what should we do now? So that means previous cycle there was no match. So what we need to do? We can just increment P here, right? P will remain same, P will be 1, we'll just increment T. That's what we are doing here. P equals to 6, P equals to 1. There is a match, so we can just increment both. T equals to 7, P equals to 2. There is a match again. We can increment both. But again, when P equals to 3 and T equals to 8, there is a mismatch. Pattern and text doesn't match because one has A character and text basically has B character, right? Pattern has A character, text has B character. So we'll have to check in the LPS table again. So we check for LPS 1. In our previous cycle we matched 2 consecutive A's, so we'll just find out the LPS value of 2 consecutive A's, which will be at first index of the LPS array. The value is 1. 1 plus 1 equals to 2. So we have moved P from third position to the second position. T remains same, but as you can see, A and B doesn't match, so we need to decrement P again. And now what we need to do, we need to check the 0th index of the LPS array, and that value is 0. 0 plus 1 equals to 1, so we move P to the first position from the second position. But again, still there is a mismatch, and P is already at the first position. We just can't go beyond that, so the only option left to us is to increment T. We have done just that. Now P equals to 1 and T equals to 9, both value matches. That means we can increment both. We have done that here. P equals to 2 and T equals to 10, but again there is a mismatch. So what we are gonna do, we'll again look into the LPS table, and we only matched one single A in our previous cycle, so we'll look into the 0th index of the LPS array. The value is 0. 0 plus 1 equals to 1. So we move P from the second position to the first position, right? And because P is already at the first position, the only option left to us is to increment T, but T is already at 10th position, and that is the end of the text. That means we couldn't find the pattern within the text, right? Let's think about the time complexity of the search that we just did. Here are a couple of things that we need to remember. While doing KMP search, we never decrement the text counter. Text counter will remain at the same position or it will get incremented. But for some fixed position of, or basically for some same position of the text counter, pattern counter might get decremented multiple times. So if we think code wise, it still feels like we have some outer loop which is getting executed for different positions of text counter. Within that outer loop, we have some inner loop which is getting executed for different positions of pattern counter. And when text counter remains in the same position, that pattern counter might get decremented multiple times, right? So if we think, it still feels like the time complexity would be big O of m into n, where m is the pattern size and n is the text size or text length. That is still quadratic, not linear. But that is not true. KMP algorithm is linear. Let's think a bit more. Here are a couple more things that we need to remember. When we increment the pattern counter, we always increment the text counter. Pattern counter never gets incremented alone. Okay. And before we decrement the pattern counter, we need to make sure that we have incremented the pattern counter. Otherwise, pattern counter will just go into the negative, right? So let's just refresh our memory. Let's go back to the earlier slides. Yeah, so we started here. We got match between text and pattern multiple times, so we just incremented both text counter and pattern counter. But here we got some mismatch where text counter was at position 5, and for the same position of the text counter we just decremented the pattern counter multiple times. And then again we incremented the text counter and there was match multiple times, so we just incremented both, and when there was mismatch we just decremented the pattern counter only. Again there was some match and we incremented both, and at the end there was some mismatch, so we just decremented the pattern counter, right? So yeah, that's the thing. So if we think, right, text length is n, so suppose we want to decrement our pattern counter in number of times in total. To do that we have to increment pattern counter in number of times first, right? Then only we can decrement it. But if we increment pattern counter in number of times, that means we have incremented our text counter in number of times also, and we never decrements text counter, right? So what happens now, because we have incremented text counter in number of times, that means we have reached the end of the text, right? So there is nothing more to search. So at most pattern counter can be incremented n number of times and can be decremented at most n number of times, right? So n plus n is basically 2n. So if we think in big O perspective, it would be big O of n, right? Because we are just removing the constant. So that is linear time complexity. So that's why KMP algorithm works in linear time complexity. So if we just think about the total time complexity, we have to add the pre-computation logic also, which is the calculation of the LPS table. And calculation of LPS table can also be done in linear time, which will require OM time. M is the length of the pattern. So total time complexity of KMP algorithm is OM plus N, which is again linear. So probably in some future video, I'll explain how can we do the LPS calculation in linear time, but I just wanted to concentrate on the search part here, and basically my intention was to keep the video short. Hopefully this has helped you to understand the KMP algorithm, the basic concept, and why the search time complexity is linear. Yeah, hopefully you have liked it. That's pretty much now for this video. Thanks, bye.